Welcome to this explainer. Today we're going to take a little journey that proves computer science absolutely doesn't have to be intimidating. In fact, we're going to completely demystify a core concept called insertion sort. We're going to translate a super simple, everyday human habit into pure computer logic. And hey, if you're a complete beginner, you are in exactly the right place. Because by the end of this, you'll see that algorithms, they're really just human intuition written down in a slightly different language.
Okay, let's dive into this. Have you ever wondered how computers take a massive, jumbled list of information and put it into perfect order? I mean, it sounds like some complex digital magic, right? But to understand one of the foundational ways they do it, I literally want you to just imagine looking at your own hands. Picture yourself holding a messy hand of playing cards that you've just been dealt. How do you naturally sort them? You probably don't even overthink it. Your brain just kind of knows what to do. Well, that exact instinct is the blueprint for the algorithm we're exploring today.
It's honestly fascinating how directly our playing card analogy connects to the formal definition of insertion sort. So insertion sort is a simple comparison-based sorting algorithm. Its core goal is to gradually build a final sorted list, one single element at a time, moving from left to right. It literally takes an element, compares it to what's already sorted, and just inserts it right into its correct position. It's exactly like sorting those cards in your hand. You take one new card at a time and just slide it into the perfect spot among the ones you've already organized.
Section 2. The Mechanics. A 5-step process.
All right, let's break down the exact step-by-step mechanics of how this works. And I promise you, following this algorithm is just as simple and physical as holding that hand of cards. Step 1. We start from the second element. Now, why is that? Well, because a single card all by itself is already sorted. We just treat that first card as our sorted foundation. Step 2. We pick up the current element, our second card, and we hold it. We call this the key. Step 3. We look at the sorted cards to our left. If they're larger than our key, we shift them one position to the right just to make room. Step 4. We insert our key into that newly opened correct position. And finally, Step 5. We literally just repeat this process. We do it for the third card, the fourth card, and so on until the whole thing is fully sorted.
Section 3. Real-world applications. When to use insertion sort.
And this brilliantly illustrates why understanding these basic mechanics is so incredibly valuable. This simple logic is powering systems all around us right now. So where does this specific sorting method actually shine? Well, as we see on the left, it works absolutely perfectly for small data sets where a simple implementation is all you really need. It's also incredibly fast for nearly sorted data, and it's perfect for online sorting, which basically means sorting data as it arrives live, one element at a time. But check out the right side. This isn't just a beginner's tool. It's actually used inside of highly advanced professional environments. It's used in adaptive systems that need to handle partially sorted data efficiently. It's heavily favored in embedded systems because it's so lightweight and has low overhead. And remarkably, it acts as this little hybrid engine hidden inside of really advanced, complex algorithms like timsort, which actually uses insertion sort to handle its small partitions.
Section 4. The pitfalls. Common mistakes to avoid. Now, I do need to shift our tone just a bit to be more cautious here. Insertion sort is an elegant tool, for sure, but because it feels so intuitive, beginners often fall into a few very predictable traps. This right here is the heavy reality check. The worst-case scenario for insertion sort is what computer scientists call O of n squared. And without getting completely bogged down in the heavy math, this simply means if you double the amount of data, it takes 4 times as long to sort. Because of this, while the algorithm is incredibly strong and nimble for small or mostly sorted tasks, it has a massive weakness. If you try to use it to sort a huge, completely backward database, it will drag your system to an absolute crawl. It's definitely not a one-size-fits-all magic wand.
So what are the actual common mistakes we want to avoid? First, like we just saw, assuming it's fast for large data. It really is not. Second, incorrect shifting logic. When you're making room for your key card, you have to shift the other elements super carefully. If you aren't paying close attention, you'll accidentally overwrite your own data, and nobody wants that. Third, starting your loop from index 0. In programming, lists start at 0, sure, but remember our golden rule from earlier? The very first card, index 0, is already sorted. You absolutely must start at index 1, the second card. Finally, a huge mistake is ignoring its distinct advantage. If you have data that's already nearly sorted, forgetting to use insertion sort means you are leaving a massive speed advantage right on the table.
Section 5. Translating to pseudocode. Formalizing human logic.
Okay, so we are now going to cross from the familiar comfort of playing cards into actual code. But don't worry, because you already understand the logic perfectly, you are completely ready to read this. Pseudocode is really just our physical actions written down mathematically. Let's map it line by line. First, we find the length of our array. That's just counting the total cards in our hand. Next, our for loop starts at I equals 1. Why 1? Because we're starting at the second card. Next, we set our key to be that card. We physically pick up the new card. Then we hit a while loop. While we look left and see cards bigger than our key, we shift them right. That's array j plus 1 equals array j. We're simply sliding the bigger cards over. And finally, when we've made the perfect space, we insert our key. Array j plus 1 equals key. So the crucial point is, you just read an algorithm. And as you can clearly see, the math is just formalized human logic.
We've taken a seemingly complex computer science concept and traced it all the way back to the way you instinctively organize things with your own two hands. Insertion sort is elegant, it's foundational, and it's quite literally built right into the devices you're using right now. But it leaves us with a really fascinating thought. If a coarse sorting algorithm is just a simple human habit written in math, what other daily automatic tasks that you do every single day could you translate into code? Just keep that in mind next time you're organizing your desk or unpacking your groceries. Thanks so much for joining me on this explainer, and keep learning.